Hello everyone, I'm Professor Harrison, and welcome back to our module on statistical inference. Today we're going to be covering the F-test, which is a tool for comparing variances, and specifically how to use it to test whether two groups have the same level of risk. We're following Bess, an investigative journalist on a cold case she can't let go, working through financial misconduct cases and applying the statistical tools that keep coming up in her reporting. Today she's covering a lawsuit where investors claim a new portfolio manager quietly changed the risk profile of their fund. Bess has a case where the complaint isn't about returns, it's about risk. To figure things out, she pulls up her case file. So far in this module, every test we've built has been about comparing means. The one sample t-test asks whether the mean equals some benchmark, and the two sample t-test asks whether two means are different. The paired t-test asks whether the mean difference is zero, but none of those tools can answer a different kind of question. Are two groups equally risky? Are their variances the same? That's exactly the question in the Ridgeline Capital case. Ridgeline is a mid-sized equity fund that replaced its lead portfolio manager about a year and a half ago. A group of investors filed a lawsuit alleging that the new manager shifted the fund towards riskier positions without updating the risk disclosures. The thing is, average returns under the two managers look pretty similar. A t-test on the means wouldn't flag anything unusual. But the investors aren't complaining about the performance, they're complaining about the volatility. They want to know whether the risk level changed, and that means we need a new tool for comparing variances. That tool is the F-test. The F-test is built on something called the F-distribution. The idea is straightforward. If you take two independent chi-squared random variables, each divided by their own degrees of freedom and form a ratio, you end up with an F-distributed random variable. So it's basically a ratio of the two variance estimates. The F-distribution has a couple of properties that are important to understand right away. First, it's always positive. That makes sense because you're dividing one positive quantity by another positive quantity. Second, it's right skewed, which means it has a long tail stretching out to the right. And third, under the null hypothesis, which says that the two variances are equal, the F-statistic ends up being close to 1. That also makes sense. If the two populations really have the same variance, then the sample variances should be similar, and their ratio should land near 1. When the ratio is a lot bigger than 1, that's evidence that the variances are not equal. So the F-test for equality of variances works like this. You set up your null hypothesis that the two population variances are equal. The alternative is that they are not equal. The test statistic is just the ratio of the two sample variances, and the convention is to put the larger sample variance in the numerator. So F equals the larger sample variance divided by the smaller sample variance. That means F is always greater than or equal to 1 by construction. Under the null, the statistic follows an F distribution with degrees of freedom equal to the two sample sizes minus 1. Then we reject when F is large enough out in the right tail of the distribution. So let's apply this to the Ridgeline Capital case. We have monthly returns under an old manager and monthly returns under the new manager. The old manager ran the fund for 36 months, and the new manager has been in charge for 36 months as well. The sample standard deviation of monthly returns under the old manager was 4%, and under the new manager it's 6%. So the sample variances are 16 and 36, and F equals 36 divided by 16, so that ends up being 2.25. At a significance level of 5% for a two-tailed test, the critical value with 35 and 35 degrees of freedom is approximately 1.96. Our F-statistic of 2.25 is larger than 1.96, so we reject the null hypothesis. The data provides enough evidence to conclude that the variance of returns changed after the new manager took over. And that's important for the Ridgeline investors. The average returns didn't change much, and a t-test on means would have missed this entirely. But the F-test catches it, because the question was never about the average, it was about how much the returns were bouncing around. One thing to keep in mind about the F-test for variances is that it's sensitive to departures from normality. Financial returns often have heavier tails than the normal distribution, and when they do, the F-test can end up rejecting too often or not often enough. For small samples especially, that sensitivity matters. There are more robust alternatives like Levine's test, which tests equality of variances using absolute deviations from the median rather than the ratio of sample variances. For large samples, the F-test is more reliable because of the central limit theorem. But it's worth knowing that the assumption of normality matters here more than it does for the t-test. So now let me cover one more connection that ties this all together. When you're testing a single restriction, The F-test and the two-tailed t-test actually end up giving you the same answer. Specifically, the F-statistic with 1 degree of freedom in the numerator equals the square of the t-statistic. So F equals t squared, and that means that for a single parameter, you can use either test and you'll reach the same conclusion every time. Where the F-test becomes essential is when you want to test multiple restrictions at the same time. We'll get into this more fully in Module 3 on regression, where the F-test is one of the central tools for evaluating whether a set of factors jointly explains variation in returns. But the core logic is the same as what we've covered today. You're comparing variability explained by the model to variability left unexplained, and the F-statistic tells you whether that ratio is large enough to be meaningful. Bess finishes the Ridgeline story and turns back to her cold case one last time. She has months of Callaway Value Partners returns split into two groups, months when the rational quant was an active counterparty and months when it was not. If someone was systematically exploiting Callaway, she'd expect to see higher volatility during the active months, more chaos, more damage, so she runs the F-test. The variance is lower when the rational quant was active, not higher, but lower. The fund's returns were actually tighter, more predictable during the exact period she expected to see disruption, and the result doesn't clear significance anyway. She sits back and looks at everything she's run in this season. Confidence interval on a counterparty frequency that was too wide to publish, the p-value of 0.07 on the win rate, the paired t-test that approached significance but didn't quite cross the line, and now an F-test that points in the wrong direction. Every test she has run on the rational quant falls just outside of her threshold or finds the opposite of what she expects. Her gut says that something's there, but all the tools in her tool belt say that there's not enough evidence to publish a story. It was almost as if whoever was the rational quant knew exactly what they were doing and how to get away with it. Wondering if she'll ever end up discovering what really happened between the rational quant and Callaway Partners, she closes her case file for the last time. So that's the F-test. The core idea is that you're comparing two variance estimates by forming their ratio. If the null hypothesis is true and the variances are equal, then that ratio ends up close to 1. When it's significantly larger than 1, that's evidence that the variances are different. Unlike the t-test, the F-test is designed for questions about risk and volatility, not about averages. That ends up being exactly the right tool when the question is whether something changed about how variable an outcome is, not whether the center shifted.